So next speaker will be the professor from Polytechnic University of Milan, Professor Liberato Ferrara. I know him for a while, and thank you for joining these sections, and the floor is yours.
Okay. Thank you, Bill, for the introduction, and good afternoon or good morning still, everybody. As a matter of fact, the work I'm going to talk is part of a, we call it holistic approach to the concept, the design, and the characterization of fiber reinforced concrete structure. Because, and we nowadays see also through these new applications which are related to additive manufacturing, it's really a fascinating material because controlling its rheology, controlling the processing, the casting, and so on, you can really tailor and tell the material to do exactly what you want to do. And one of the issues that we encountered when we started working with this material was exactly the issue of fiber dispersion. As a matter of fact, you can see that there has been a lot of progress between workable concrete and self-compacting, self-consolidating concrete. As a matter of fact, I started studying the orientation of the fibers when I looked into self-compacting concrete. And which was the occasion? We worked with an Italian company on the production of precast elements for roofs or for girders. Very thin elements where the fibers were instrumental at removing completely the secondary reinforcement for shear, for transverse flexure, and so on. You only have the main pre-stressing tendency in the longitudinal direction, but then all the other kind of reinforcement, except for some local one in the edge regions, was completely removed. But in the end, when we made the first trial test on full-scale mock-ups, we encountered unexpected failure modes. Well, partly was because we had very thin slabs, so we ran into buckling problems, which are not so common in concrete structures, but was also because we had poor dispersion of the fibers. And, well, this is quite an old work, but we drilled the cores, and we cut into slices, and we X-rayed them, and we realized that, for example, this is the same core, this is the bottom part, this is the top. There were no fibers on the top, because with the vibration, the fibers go down, settle down. But you can imagine if you have these wings here, which are subjected to lateral flexure, you need the reinforcement of the top because the moment is negative there, so you need some reinforcement there. With no fibers at all, you had first cracking, immediately localizes in a stable manner, and you break it. So we worked out with the company, we developed a self-compacting fiber reinforced concrete, and we made the element, drilled the cores, this is the bottom and the top part of the core, and we realized that avoiding the vibration as self-compacting concrete allows to do us, there was a good dispersion of the fibers. So if you go back to your handbook of fluid mechanics and look for the Bingham fluid model, which is the one that we usually employ to describe the behavior of concrete in the fresh state, you realize that when you have a fluid with a low yield stress like the self-compacting concrete is, you might have a profile in your free casting flow, you might have a profile of stresses like this, which if you implement the constitutive relationship below the yield stress, the strain rate is 0, but when you overcome it, the fluid starts moving. So if you integrate this, you get the velocity profile, the drag forces are similar. So if a fiber is crosswise to the flow, you have it aligning because of these forces. This is not the case of conventional vibrated concrete, because in that case the yield stress is very high, so what you have is a plug flow and you simply push rigidly ahead your fiber. So with this self-compacting concrete low yield stress, you tend to go back to what is the theoretical profile for Newtonian fluid. And we wanted to verify this, so with my colleague, Professor Nilüfer Özgürt, who is now at Boğaziçi University in Istanbul, we did quite some work with some mock-up castings. We had the flow in one direction to align the fibers. We cut sections at different distances from the flow. And we analyzed the micro images, reconstructing the elliptic cross-section of the fibers and calculating the angles. So we ended up with available projected length of fiber available along each direction, which we call the orientation number. And you see that along the direction of the flow, you have about 70% of effectiveness of the fibers. You cannot avoid some three-dimensional also in the other direction. But 0.7, it's quite good. So then we said, okay, but this is quite time-consuming. If you have to go to the industry, you need to have non-destructive methods. So we worked with different methodologies. We tried the thermal methods. We worked, when I was in the US at Northwestern University, we worked with impedance spectroscopy. Then we ended up with this magnetical inductance method. Very simple. This is the first version, very rough, of our sensor. Was simply ferrite, old-style telephone handle. I don't think there are any more telephones with that device like that. There is a winding here. The electric current passes, generates a magnetic field. And when you lean this probe against the concrete slab, you close the circuit, and the sensor feels the alignment of the fibers, because according to this alignment, you measure a different inductance if the fibers are parallel or orthogonal to the flow. You can use the mixer rule, linearize it, because the content of the fibers is usually in the range of 1 to 2% by volume. And so through this method, we were able to have an idea of the local concentration and the alignment of the fibers. We did some larger casting. These were slabs 1 meter long, 500 millimeters wide. We tried with different contents of fibers. We verified the alignment. But most of all, we wanted to quantitatively calibrate the methodology. So we had some volunteers. We cut the slab into squares. We crushed it before we made the magnetic survey, but we crushed each tile that we obtained from the slab and separated the fibers and measured the content. So based on through this, we calibrated the correlation between the measured magnetic inductance and the content of the fibers. And you can see that we have quite good predictions, because the non-destructive method gave us 108.7. Here you have 109.5, 1.1. 0.9, so the calibration was quite good. As a matter of fact, what you can see here, and probably the presentation previous also said that, as long as you go farther from the flow, you have some fibers who settle down and are no longer driven, so the content of the fibers tends to become a little bit poorer. And then, which was the further implication? The further implication is how this translates into the mechanical performance of the UHPC, because if you have alignment of the fibers, you can expect that the performance of the material in that direction is enhanced. But on the other hand, on the orthogonal direction, the performance of the material is weaker. So you, in a sense, have a benefit, but you also lose the isotropic assumption of the material. You must accept that you cannot design your material any longer as isotropic. And we cut some beams, parallel or transverse to the flow. We tested them, and some exemplary results are this. These are the beams with their longitudinal axis parallel to the flow, so parallel to the most favorable alignment of the fibers. And these are the beams which have the alignment orthogonal to it. We removed the region where the fibers were casted, because there you have turbulent and random orientation. So, as I said, there is a pros, because in this direction the material has a very good performance. There is the cons, because in the other direction the material is weaker. And then we made different tests, and we calibrated, so we had the correlation between the different residual post-cracking strengths at different crack opening widths, which you can select as relevant for your design, and we correlate the orientation densities. And some of the results also inspired the formulation that now you can find, for example, in the FIB model code or Eurocode, where you can have an orientation factor which affects your design post-cracking residual strength parameters for fiber reinforced concrete. So then we made a step back. We said, okay, we know that we can align the fibers thanks to the flow. We know how to monitor that. So the question was, and how can I design the flow so that I got the orientation that I want? So we moved, in a sense, from the structural design to the process design. We wanted to model the process of the casting. These are some snapshots. I'm sorry, I tried to put the movie, but the system did not support it, so I had to extract some snapshots. We developed an in-house particle finite element-based code for computational fluid dynamics, and we decided for computational cost effectiveness to consider the fiber reinforced concrete as a homogeneous fluid. We know that it's not correct, but we thought that this was a good approximation between computational efficiency and the reliability of the information that we could get. We started modeling a very simple problem that we also tried on the experiments. This is a beam according to the European standard for testing FRC. So we put a V-funnel, the one that you use for SCC, in order to limit the human intervention to the casting. We filled the V-funnel. The volume is more or less the same, so we were lucky. Fill the V-funnel, open the shutter, and have the flowing concrete filling the mold. So we tried filling on one side, filling on the other, and we modeled this process. And we also applied this to model some slab casting. We had one slab cast from the corner, and these are the flow lines, the velocity vectors of the flow. So we wanted also to see how internal boundaries affected the flow, so we put a shutter here, and these are the velocity profiles. So what we did, we performed the magnetic survey on these slabs with our probe, and you see in blue we have the front of the flow lines, and in red we have the direction of the major fiber alignment in the flow. So in this case, with the 2D flow, you lose the one-directional alignment because you have no longer the constraints of the boundary, and what happens is that the fibers are driven parallel to advanced fluid front. In a sense, it's good also in this case because in a 2D structure, in a slab, you do not want a one-directional alignment if you want to exploit the slab action, but you want an alignment which replicates what we had here. And also, well, this is nice color. At the end, we tested, this work was done at Laval University with Luca Sorelli. We tested these slabs. With DIC, we reconstructed the cracks. You can see the cracks are in purple, and in yellow, we developed an algorithm to plot the direction, the main direction of the fiber alignment. Obviously, if the direction is yellow, the material is stronger in this direction, but it's weaker in the opposite direction. So you have cracks exactly formed in that way. So which was the final step of our work? We wanted to bring it to the real job site. So the chance was a European project in which we wanted to use UHPC. That was for durability and self-healing reasons, but we tried to plug in also this work. So we designed this. This is an ordinary reinforced tank. We designed these two additional tanks. These are cantilever walls made of UHPC 6 centimeter thick, so you simply cast them vertically. And these are precast UHPC walls, 3 centimeter thick, which we cast horizontally. We tilt them up, and then we fix it with these cast-in-place columns or buttresses, if you like. So this is an image of the basin when we made the validation test. And actually, we monitored the dispersion of the fibers. What we did realize, for example, that casting vertically, this is a 1.5 meter tall section, cast all in the same time. There was, in the top part of the slab, there were some segregation of the fibers. You cannot avoid that. So this was also, a learning by doing, in the sense that probably we said in the end, and we recommended for the construction, because, it's a district in geothermal basin in Italy. They have several of these tanks, so they construct more. We recommended them, if you want to build just casting layers, use some dowels to connect to avoid this segregation. And which was the outcome? The outcome was that the shrinkage cracks, this is an 8 meter long wall. UHPC has quite some shrinkage, but we only observed some shrinkage part in the top 10 or 20 centimeters of this slab, just because this was the zone poorer of fibers, where we were also lucky because, as you can see here, then due to the self-filling capacity of UHPC, those cracks completely closed. On the other hand, for the horizontally precast slabs, before installing them, we made a complete survey of the fiber dispersion, and thanks to the calibration that we previously performed, you can see here we got a good average constants of the fiber content in the slabs. And I will say the basis is now under operation for about 2 years with no problem, so we are quite happy about that. So just to come to the conclusion, rather than conclusion is a summary. So we developed this non-destructive magnetic-based method for the monitoring of fiber dispersion and orientation. We validated and calibrated at the lab scale, and we also associated it with computational fluid dynamics prediction in order to design the casting process so that we have the fibers aligned along the direction that we want. In a sense, you can make a computational fluid dynamics prediction and match it with the classical finite element analysis so that the fibers are aligned along the direction of the principal tensile stresses in your structure. This will be the optimal outcome. And we applied it and demonstrated its scalability and feasibility also to a real case study in the industry. Thank you for your attention, and thanks to the sponsors as well.